So just to practice our proofs, like I said, this is on your formula sheet. Anytime you see a secant squared, you are allowed to change it to tan squared theta plus 1 without showing any work. If you have a tan squared theta, you are allowed to change it to secant squared theta minus 1 without showing any work. Because you see it's pretty easy to move the 1 over to the other side. Any of the formulas that you have, one little mental math change, you are able to change without showing any work. Question?
Did Connor go in the hallway?
Connor is working on, he's actually doing his quiz.
Okay, I just didn't know if you
Yeah.
grabbed that.
No, you thought maybe I forgot about him completely. I can understand you thinking that. But no, I didn't forget him. No, actually, I just like you and better than Connor. That's what's invited only one back. Okay. So yeah, so if you saw a tan squared theta from now on, you could just change it to secant squared theta minus 1, and maybe that would make your proof easier. We're going to see some situations where that might be the case. Okay, but for right now, we're going to say, well, why is this true? Well, if we did our regular proving strategy, if tan is sine over cos, tan squared is sine squared over cos squared. And I still have a plus 1 here. And over here, if secant is 1 over cos, you're allowed to change secant squared to 1 over cos squared. This is a proof, so we have to work on left side and right side. After changing to sine and cos, the next part of the strategy is to get both sides to be one fraction. The right-hand side is already one fraction. But the left-hand side is adding, so I have to put these fractions together. What's our rule for adding fractions? Need a common denominator, so I'll multiply top and bottom here by cos squared theta. And that will get my common denominator of cos squared theta, and my top is now sine squared theta plus cos squared theta. Now, in almost all of the proofs that we've done up so far, if you got a single fraction on both sides, you were done. But these aren't the same yet. They're very close though. I hope you can see, right? You have this on your formula. Sine squared theta plus cos squared theta is equal to 1. So you're allowed, anytime you see that, because it's on your formula sheet, you're allowed to change it to 1. And now our left side is equal to our right side. And we're done our proof. Okay? You could do the same thing with 1 plus cotangent squared theta. It's equal to cosecant squared theta. But now these two get added to your formula sheet as the Pythagorean identities. And you don't have to prove them. You just get to use them from now on. Anything that's on your formula sheet, you can use from now on. In fact, anything you can do with one rearrangement.
Hi, could I please have Isabella to the office?
Yeah, she'll be right
Thank
down. Right. Anything with one manipulation you're allowed to do. Anything more than one manipulation, you have to show your work. So you can't just be like that person and say, ladies and gentlemen, it's obvious. This is true. You have to show work if it's more than one step. So I couldn't do in one step tan squared theta minus secant squared theta equals minus 1 because I moved two things. Then I'd have to show more work. But just doing one thing you can do without showing work. Okay? All right, so now we are going to look at this with some proofs. And when we might use these identities. Now I'm going to erase B. Oh, there we go. I'm going to draw my line. I'm going to draw a little bit of an angle so I have enough half and half space here. We're going to prove this first one. So I looked at the question. part of proofs and advanced strategies that we're going to get into, you're going to take a little bit of time to analyze it. Okay? In this one, I see a cotangent, I see a tangent, I see a cosecant, and I see a secant. But I do not see anything squared. So right now, we just got those three new identities, sine squared theta plus cos squared theta equals 1, which wasn't new, but tan squared theta plus 1 is secant squared theta. We have those new ones, but you can only use those if you have something squared. This one doesn't have anything squared. In fact, we could have done this proof yesterday. Use your regular strategy. Can you change everything to sine and cos? Yes. What's cotangent? Cos theta over sine theta. What's tangent? Sine theta over cos theta. What's cosecant? 1 over sine theta. What's secant? 1 over cos theta. So we could change everything to sine theta and cos theta. Then, as part of this strategy, we want to get a single fraction on both sides. The right-hand side, I think, is the easiest. How do you multiply fractions? Multiply the tops, multiply the bottoms. Perfect. I have a single fraction. The left-hand side, you're adding fractions. How do you add fractions? You need a common denominator. What's the common denominator between sine theta and cos theta? Sine theta times cos theta. So this one, I'm going to have to multiply by cos theta and cos theta. And this one I have to multiply by sine theta and sine theta. And again, you get lazy and forget a theta once. It's an E3 error. So now I've got a common denominator of sine theta and cos theta. I'm kind of excited because does not matches the denominator on the right side. But on the top, if I multiply cos times cos, that'll be cos squared theta. If I multiply sine times sine, that'll be sine squared theta. I'm very close now. On both sides, you see that my denominators are the same. The only thing different is my numerators. So then you go, is there something I can change? Cos squared theta plus sine squared theta? It's equal to 1. That's our big idea from chapter 6. So you can just change it to 1 without showing any work because it's on your formula sheet. And now they're identical. We can say my left side is equal to my right side, QED. And our proof is done. Is that enough time? Sorry, everybody good? Almost. All right, next proof. First of all, this next proof should appear to be scary because it has a cube in it. That should make it scarier already. And I'm going to tell you in this question that using our main strategy would be somewhat painful. You could change everything to sine and cos and get a single fraction. And it will work eventually, but the proof might take a long time. So sometimes now we're getting into advanced strategies. There are some strategies that make it shorter. First of all, I see something squared. I see cosecant squared right here. Anytime I see something squared, my mind should go and say, maybe one of these new formulas would be helpful. And I have a cosecant squared theta, so I look at my formula sheet, and I'll just write it here off to the side. On our formula sheet, we have that cotangent squared theta plus 1 equals cosecant squared theta. That might be helpful. And one of the strategies in identities is looking at things that might be helpful and making a decision of saying, Should I try that or no? And if you're like, maybe I should. Do you know what's really nice about changing the cosecant squared to cotangent squared plus 1? Do you see that everything you have then is with cotangents? And if everything's cotangents, it might work out really nice to show the left side is equal to the right side. So I'm like, I really like this. I'm going to see what happens if I do that. I take the cotangent theta, and then where the cosecant squared theta is, I still have minus cotangent theta here. I substitute in cotangent squared theta plus 1. Now just do all the algebra you know. Like, hey, wouldn't I have to distribute this if it's multiplied? What would that give me? That would give me cotangent cubed theta plus a cotangent theta, and then I still have a minus cotangent theta. I'm like, woo! Those would go away. That's kind of nice. What would that leave me with? Cotangent cubed theta. And this proof ended up being nice and short. So there's an advanced strategy one. Had you changed this to sine and cosine?
Only one council.
Two, sorry.
Only 2 rows, so it's not great. I'm just kidding. Oh. All right, so this is an advanced strategy. We could have changed it to sine and cosine, but then it gets a little bit messy. It would work, and you would, if you choose a messy proof and it's all good, 100%. But some of you are going to be like, I wrote 4 pages in my proof, I got 100%. You look at your friend and they wrote, I did 2 lines and I got 100%. You're kind of like, ooh, that seems like less work. I might like the shorter one. All right, I'm going to add a part C to this one. And I'm just going to erase this part here. That's as if I wanted to make it even harder. Tan to the 4 minus secant to the 4 equals minus tan squared minus secant squared. And the 4s, when we see them, we should get a little scared. Okay, but I see a tan squared and I see a secant squared, and I'm kind of excited because that's on my formulas over there. Okay. This one also has an advanced strategy that you already know, but we haven't done in a proof yet. Something you already know how to do in math is, you know how to factor. And in particular, you have factored differences of squares in the past. Just a little reminder, x squared minus 9, that's x plus 3x minus 3. Remember that? That's called the difference of squares because the x is squared, 9 is 3 squared, and difference means subtract. That's why we call it difference of squares, because you're actually subtracting 2 square numbers. When you have a difference of squares, it usually makes sense to factor. So one of the things you're going to be looking for in proofs from now on is looking for differences of squares, because then you might be able to factor. The right-hand side is not a difference of squares because of the extra negative, but the left-hand side is. And so, if I take the left-hand side and I factor it, to get tan to the 4 would be tan squared and tan squared. Wow, that's true. To get secant to the form would be secant squared, and a difference of squares would make 1 plus and 1 minus. Now I have two factors here, one on the right. They all involve tan squareds and secant squareds. And we have the following formula on our formula sheet. We have that tan squared theta plus 1 equals secant squared theta. One strategy we could do here is wherever you have a secant squared, you could replace it with tan squared theta plus 1. Everywhere. That will work, and it's a beautiful strategy. I'm going to do it a little bit shorter. Okay? So I actually really like that strategy. Change this secant squared to tan squared theta plus 1, change this secant squared to tan squared theta plus 1, change the last secant squared to tan squared theta plus 1. Simplify everything and see if you get the left side equals the right side. You will. It'll work out beautifully. I really like that as a strategy. But I'm going to do it a little bit shorter. And I'm going to look at all three of these. And in my head, I'm going to change secant squared theta to tan squared theta plus 1 only in one of them. So I want you to look at all three. And if you played around mental math by rearranging things here, is it ever possible to get a tan squared theta plus a secant squared theta on the same side in that formula? And you see the answer to that is no. If you move the secant squared theta to this side, it'll be minus. Or if you move the tan squared to that side, it will be minus. This one doesn't match up. I'm going to leave that one as it is. Look at the next one. Could I get tan squared theta minus secant squared theta on one side of that equation? Yes. So this is the one. I would keep this one the same. And this one, instead of the secant squared theta, I'm going to put brackets and replace it with tan squared theta plus 1. What will that do? This doesn't change. If I simplify this, you see that you get tan squared minus tan squared. That'll go away. And if you distribute this negative, this whole thing will just be a negative 1. Would I be allowed to change this directly to minus 1 without showing work? No. Because mental math-wise, it takes two things. You have to move the 1 over and the secant. That's two things you have to show your work at. So I had to show that extra step. And now when I distribute this negative, I get negative tan squared theta minus the secant squared theta. That matches up perfectly. My left side is equal to my right side. Q, E, D, all done. Another advanced strategy, looking for differences of squares. So I think, yeah, because without the next advanced strategy, the next question is actually impossible. So what do? Do I show you all the, okay. I'll get you to circle questions. You can circle 3, 5, 3, 5, 6, I, 7, I, 9, I. That's probably because the first part was a verify. You should get good at verifying too, but the proofs are more important.